Okay, can you? Yep, it's working. All right, good, 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 good. All right, so you've got me for 2 hours. Yay! That's right. So I have 150 slides. I'm going to start with the good news. So my talk is not 2 hours. So there is a little of a surprise for you guys, right? I think about 45 minutes into my talk, right? You'll get rid of me and it will be much more fun. So that's the good news, but the bad news, we're still here. Well, some of us, me and June said, I know everything about your talk, so he just left. That's okay. I was his postdoc. Maybe he does know everything about my talk. Um, so we kind of, well, I personally debated whether or not I should talk about this, but I do believe that that it may, well, I mean, it's worth a shot, right? Okay, so we were talking about, let me just write this word, about B-spline basis, right? And we know what B stands for. Well, some of us think it's the Bohr, some of us think it's the most beautiful splines, right? Yes, okay. So I will be talking about and I know for sure what it stands for. It stands for better than B-spline basis, right? So hopefully you will believe me. All right, so before we get into that, it's the last talk. Something is wrong, Carla? Okay, no, turn it on because I'm gonna write on the board for like 5 minutes, okay? So it's the last talk. So half of you are asleep, half of you just woke up like John. So he's gonna get the first question, right? So I will start with a problem for Calculus 1 students, right? Which I like very much. So let's see. We are going to think about a spline, a piecewise polynomial on 2 subintervals, right? And I want to build a spline. And if I ask Carla or Tom, which I won't, they will suggest building a sequence of points called xi or eta and building a B-spline basis. But we're in calculus 1, so we don't want to do that. We don't want to build anything beautiful. We want to build something that works, like very similar to the previous talk. So, and of course, everybody uses parabolas, right? I want to build a piecewise parabola, right? And I'm going to ask you questions and you're going to give me the answer. You can shout, you can show the number of fingers, right? All right, so my first parabola is going to be here and it's going to be A1 plus B1x plus B2. Oh no, that's already wrong, sorry. Yeah, you know, nobody nobody jet lagged should be talking on the first day, but so let's start with B0, that's fine, I guess. B0, right? Okay, 3 parameters like statisticians would say, and I'm not gonna say what they are, but the number is 3, right? And then the second parabola is going to be, let's say, A0 plus A1x plus A2x squared. So that's my second parabola. I have 3 more parameters, right? So if I say nothing else and I want to build a piecewise function, which is a parabola on the first interval and another parabola on the second interval, and I don't want to do B-splines, so how do I do that? Well, right now I don't have any information, right? I'm going to just say that let's use linear algebra. What is the dimension of this space? Because I'm building right now as, I don't know, my something -1 maybe. 2. I'm going to call it like that for some reason. So the dimension of the space is 6. Why? Because I'm going to use the degrees of freedom thing, right? There are 6 degrees of freedom, right? Good. We can choose 6 parameters and there will be 2 parabolas. They have no relationship whatsoever, but it's still a spline, right? Okay. And what is the basis? I mean, it's up to you. You can choose any basis you like, but that's a vector space, right? Dimension 6, okay? So now I want to say, I want to build a continuous spline, right? What's gonna happen? It's a subspace, right? The dimension goes down by how much? Show me the dimension on your fingers. What's the dimension of the space if I now want it to be continuous? It was 6, what's now? Great, John is up. Okay, I knew it. Great, so it's -1 condition, right? There's one equation. Okay, great. So the dimension of this would be 5, right? What's the basis? I don't know. We can build a B-spline basis if we want to, I suppose, right? We can do that, but we won't. So then, and how would you, fine. So we need 5 pieces of data. Now we're going to think about data, right? So we need 5 pieces of data to build this thing. What kind of data doesn't matter. We can use flies, whatever data, we can build it. If I want to make it smoother, right? And like Carla did, I'm going to be putting this zero thing. This is my smoothness and this is my degree. So if I want now to match the derivatives, right, then the dimension will be 4. Very good, excellent, 4. Now this is a more realistic situation, right? So let's think about what data could work here, right? Like reasonable data. Okay, so Uli is falling asleep. Uli, suggest some data.
Yeah, you could choose 4 points on the left.
That's great. That's a wonderful suggestion, Nate. We could choose 4 points, exactly, right? Or we could choose 3 points on one interval, 1 point on the other, right? But the idea is that if I'm choosing 4 points on one interval versus something more reasonable, I would probably choose a different basis, right? To make the computation easier. So depending on what kind of data we're choosing, we're probably going to adjust the basis. So what I'm trying to say here is that for this computation, clearly it doesn't matter what basis we're using, right? But in general, the basis should probably depend on the data. We shouldn't just take some functions, even if they're beautiful B-splines, right? And for some reason say, this is what I want. So a reasonable data here, for example, for finite element people, which I won't say a word about, but at least it's a symmetric data, right? You could put the value here, the value here, and the value here. That's not enough, right? It's only 3. And then add maybe a derivative here, right? I don't know how to say that. Let's add an arrow. They usually, I think they use arrows, right? That's 4. I'm not going to think about unisolvency. You can prove it. It's calculus 1, right? But something like that. And so which basis shall we choose? Shall we choose this basis, just, some standard or cardinal basis? I don't know, maybe, right? But maybe not. Maybe there's a better one. And so that's basically where I'm going to begin, because B-spline basis, no matter how beautiful it is, first of all, as far as I know, it's not always even defined for arbitrary triangulations, right? At least, you don't know how to build it. And it's a computational adventure because you have to pre-compute it and store it. And then it is not necessarily your data feeding. Okay, so let's, I'm not gonna go again over all my slides, but hopefully I will convince you that there are some better choices here. Oh, I think I'm moving in the wrong direction because that thing is not working. Do I need to push some other button? Oh, okay, well, I can do that, yeah. Oh, now it's working. All right, great. So Min-Jun left, but he is the author of the book where these are the main tools, basically. And if you're interested at all in looking at Bernstein-Bezier BB basis, then there is a software for it, which again, I won't talk about, but you can explore it or ask me later, okay? So that's how splines look, essentially. So this is from the algebraic standpoint. I will say a word just in case, because we don't have any algebraists. We did not invite them. We kind of excluded them. But to them, splines are not linear spaces. They are modules over polynomials. So in other words, if you take a C1 spline and multiply it by any polynomial, it remains C1. It's calculus 1, right? Product rule. So they look at it as modules. And so they don't have to be defined even over triangulations. There is work on semi-algebraic splines over certain, partitions defined by algebraic curves. So it doesn't have to be straight lines. But I will concentrate mostly on the triangulations. Carla already introduced the notation for SRD. The pointer is working. So D is the degree, and the smoothness is on the top. The degree is on the bottom, okay? All right, so let's just, sorry. That's just a picture. All right, so if I were to ask you now to do a similar computation to this on 2 triangles, right? you would have done it. It's not calculus 1, it's calculus 3, but it is doable, right? And you don't need any B-splines for that. You can just write the polynomial in general on one triangle using Cartesian coordinates, and then a polynomial using Cartesian coordinates over a different triangle, and then write a couple of equations, and everybody would have a spline by the end of the day. But if I were to ask you to do it on, let's say, this triangulation, then I sincerely doubt that you would have been done by the end of my talk, because this computation is much more difficult, and no B-splines is gonna, well, B-splines exist on that, right? So yeah, you could do that, I guess, right? But it's definitely not worth the time that is. All right, so what's a meaningful basis for us? And again, Carlos said a little bit about that, Tom said a little bit about that. It's local. In other words, if we are changing the construction over one triangle, or in general could be something else, but one domain piece of domain, then it should really affect only the closest neighbors, or even nothing at all, which is impossible, of course. Then we do interpolation, we do quasi-interpolation as well, but nothing is preventing us from, not interpolating and doing something else. In other words, pursuing some other properties. I will concentrate on interpolation to show you the meaning of the coefficients, but in general, again, it doesn't have to be interpolation. It can be something else as well. And then the main point to me would be to check the smoothness somehow locally. In other words, just by looking at it, I want to see if they're smooth. So if, for example, right here, I'm going to write something like 2x squared, minus 1, and here something like 3x squared plus 1, I have no easy way of saying smoothness. I would have to take the derivative, and see if they're equal to one another. I mean, it's easy, but it's not obvious. So I want something where I can see it almost immediately. So these are my basic requirements for the basis, okay? And we're gonna start with a Cartesian standard. Let's use the word standard, like algebraists do. So this is a cubic polynomial written in the standard basis, in XY basis, right? And I'm gonna ask a very stupid question, I guess. My first question would be, what is X? Really, right? I know some of you know the answer to what I want to hear, but if you don't know what I want to hear, think about it. What really is X? And it's hint, it's not a random variable, right? That's a hint. So what is really X for this polynomial? Or what is really Y for this polynomial in this form, right? Right, okay, keep wondering, but so I rolled the coefficients with certain subindices, right? And that's an easier question. If you look at these points on the left, you will see that the number of points is exactly the same as the number of coefficients, right? Which I think is 10. Although Bert said mathematicians cannot count, but it's 10. So if I, for example, don't think about it too hard, right? But like if I point at this, right? Which coefficient do you think is associated with this point? A00, right? For some reason, right? Okay. And if I point at this one, A10, right? There's no doubt. Why? I mean, who knows, right? But your brain is telling you that, right? Okay. And like this one would probably be, I can't really reach the other one. I'm not sure my pointer works, but you get the idea, right? So the coefficients are somehow in your brain associated with the points, obviously, right? And there are connections, obviously, right? Okay, so is that a meaningful basis for us? In other words, do these coefficients really tell us anything at all about the polynomial? I'm gonna ask you. So what does it tell you about the polynomial? Do they say anything? Like if I know that, let's say if I'm saying that this coefficient is, I don't know, 5, it tells me something, right? What does it tell me? Not approximation theory people. We're checking. So what does it tell me? What's 5? 5 is what? It's like everybody knows, right? 5 is the value of the polynomial, right? It's 0, 0, right? Okay. And if I say that the second coefficient is 1, This is harder because you have to take the derivative, probably think about Taylor expansion, right, at 0, right, and say this has something to do with the first derivative at 0, right? There's a formula for that, obviously. And this coefficient will have something to do with derivative of order 1, 2, 3, right, at 0, okay, right? All right, so in other words, what I'm giving you right now, when you're looking at these coefficients, if you know the numbers, you know everything you ever wanted to know about the polynomial at 0, right? But why would you want to know that? If you're trying to glue two polynomials together along maybe the diagonal, right? Like, why would you care about the value at 0? You don't, right? So the dream is, can we somehow extend this Taylor expansion and make these coefficients a little bit more meaningful and make, for example, this coefficient, let's say this one, right? Tell us something about the polynomial, not at 0, but on this line, perhaps, right? Or even maybe at this vertex, but definitely not at 0, because 0 has nothing to do with that line, okay? So this basis, which algebraists love, it is not a very meaningful basis for practical purposes if you're trying to build a neighbor which you want to glue next to this one, okay? All right, so we are going to, so and then worst of all, if I change the triangle, right, then the standard form doesn't change. It looks exactly the same. And now, of course, if I ask you to associate, let's say, this point with some coefficient, you will be like, oh, what is she talking about, right? And it's complete nonsense. There is no association whatsoever. I can still put my 10 points, right? But they're not associated with these coefficients in any possible way. Moreover, they still tell me something about the behavior of this polynomial at 0, but 0 could be over there, right? So I don't really get any information about that whatsoever. Okay, so what do we do to alleviate this? We do something really stupid to begin with. So what I did here, I multiplied it by 1 to the power that made it cubic, right? So in other words, I'm homogenizing this. So this 1 is now cubed, and I know it's a stupid operation, but at least now it looks like semi-homogeneous. And instead of x and y, remember the question, what is x and what is y, right? And they're not random variables. Now at least you can see that there's sort of like, well, you can say linear forms, so you can say affine forms, right? In some sense, okay? So in other words, x is somehow associated with the y-axis, right? This is where x is 0, and y is associated with the x-axis because that's where x is 0, and 1 is, well, that's the problem. Who knows what y is? But x is the y-axis and y is the x-axis. So what are we missing here? Well, we're missing here this line, right? So if we can probably add this line, we can get more information. And basically, that's what it is in some sense. We're going to change the affine forms associated with the triangle to something more meaningful. Okay. Oops, sorry. All right, so here, right? So again, if I change this, then everything is gone. So we're over here. All right. So what we're going to do, instead of using x and y and 1, we're going to use the boundary of the triangle, and each one of them is a linear form or affine form. Choose the language that you like best. So it has an equation, right? Like an equation in x and y coordinates. And we're going to choose this equation as a coordinate. So these are not unique. We can normalize them, we know that, by essentially requiring that the value of B3 at the vertex V3 is going to be 1. And if you can imagine this picture, it's actually, this becomes, if it's 0 here and if it's 1 at V3, it becomes a plane, right? It's a piece of plane, and it is an affine form. And that's what we're going to use instead. So in other words, we're going to write the same polynomial, remember, homogenized, right? Instead of 1 cubed, I have now B1 cubed, and so on and so forth. The subindex 1 stands opposite vertex. So B1 is opposite V1, and so it goes. So what is it? It's a change of basis. Linear algebra tells you it's a change of basis. You can produce a matrix for sure. And my claim is that this basis is more meaningful. Well, first of all, it's sort of homogeneous, which is always better because I plus j plus k will add to 3 in my case every single time. Notice that B1, B2, and B3 are not linearly independent because I have three of them, but that's not a problem whatsoever, right? So why are they more meaningful? In general, what we're doing, we're replacing a polynomial, the standard basis, with something else, which we're going to call BB form of a polynomial. It looks a little more complicated, but again, remember, these are the equations of the sides of the triangle that you're working on. So it's a simple linear equation right there, each one of them, okay? And this is the normalization factor, which makes it partition of unity in the future, okay? All right. So a couple of things before I proceed any further. This basis depends on your choice of the triangle. If you change the triangle, you choose a different basis. So in other words, your basis goes with the triangle. And if we're building a space of splines, there will be a different basis for each triangle, okay? That's a heavy price, but on the other hand, there are benefits here. So what are the benefits? Okay, so let's go for the benefits. So this is some, I mean, I'm gonna just probably, they're known also as aerial coordinates. I'm going to skip that. And of course, they're barycentric coordinates with respect to the triangle. These are like basic facts from geometry, which are not very important for us. So the points that we were talking about, so first of all, they're associated with the points. Remember like how your brain put the association of the coefficients with the points right away, right? That association exists. And we're formalizing it here by saying that each basis function is associated with a certain point, which again, your brain will place it right away, but mathematically, here's the formula for you, okay? So that is the formula for the domain point. So we have 10 here, for example, and each one, well, we can say a little bit like they're kind of like weights, right, in some sense. So the higher, for example, I is, the closer it is to V1, and so it goes, right? And they're called domain points for us. So to people who work with splines, when we think about a basis function, we immediately think about a domain point. So we don't think about basis functions. We think about domain points instead because we can visualize them. We can see where they're located. And by the way, if you think about 3D, 4D, it's the same, right? Because this is a triangle, it's a simplex. So if you think about a simplex, you do the exact same thing and you get the same domain points, you get the same basis. These functions, I'm not going to prove it, but they're linearly independent, they span, the dimension is the same, and so on and so forth. So this is completely dimensionless. In other words, you can write this, if you do a multi-index, you can write it dimensionlessly. All right, so this is the domain points for 4. So the degree of the polynomial, I mean, I personally just count the number of points on one edge. If it's 1, 2, 3, 5, so it's -1, it's degree 4. You can do the combinatorics and compute the dimension. All right, so now here is, let's start here. So I'm going to try to convince you why this is a more meaningful basis. And in order to do that, I need to introduce the notion of combinatorial distance, okay? And it's exactly what your brain is already telling you. So for example, this point, if I'm looking at this point is at distance 1 from this vertex, right? I mean, it's pretty clear, right? If I look at this point is a distance 1, 2 from V1, right? And distance 1 from V2, okay? You just, basically you count the layers. And you can write the combinatorics, but don't think about it. It's 5 o'clock, so just look at the picture, you can count, right? So also you can think about combinatorial distance from an edge. So for example, this point is at combinatorial distance 1 from V1, V2, or V3, V4, V2, and so on and so forth. But again, it's not a Euclidean distance, it's a combinatorial distance that depends on the degree of the polynomial, right? Let me see if I have bigger. I'm gonna go ahead and look at the bigger picture. So let me see if this point, right? I'm looking at this point is combinatorial distance 2 from this vertex, and it's combinatorial distance 1 from this edge, right? Okay. So good. Okay. We can also say that any of these points is at combinatorial distance 0 from the triangle itself, if you wish, right? But this notion goes to higher dimensions as well. And again, combinatorially, you can do the count of this, IJK, the multi-index count, which is boring, but if you have to write the proof, you can always do that, okay? All right, so I did that. Great, so I think control points, so what's a control point? A control point is the coefficient that is in the representation of the polynomial written as a z coordinate in the vector over the domain point. And I do have some pictures somewhere. Yep, right there, okay? So in other words, let's say this is a domain point at the vertex. That's not a good example. Here is the domain point, that is the control point. So this is the coefficient of the polynomial. It doesn't interpolate, so the polynomial itself is that colorful surface produced by MATLAB, right? And this point is not on it, just this one is also a control point over one of the others. Well, it's just the last definition I think that I need. Okay, so here we are. Let me go back. Okay, so if we're looking at the Cartesian or standard basis, right, then we already know that these coefficients are everything you want to know about the behavior of the polynomial at the origin, right? Like certain derivatives of order d at 0, 0, which are irrelevant to our problem. So if we're looking at the Bernstein-Bezier form, then we want to know what is this coefficient and how it is related to the information of the data that is located somewhere along on the boundary or inside of the triangle. And basically, pretty much, so again, this is your Taylor expansion. And the question is, can we somehow extend this Taylor expansion information to more reasonable points using the Bernstein-Bezier form? And the answer is basically yes. And that is the rough answer. So if your domain point is a distance, combinatorial distance t from a face, then it is associated with the derivative of order t on that face. Not at 0, not at some other vertex or whatever, but from that face. So let me just look at a couple of examples. So for example, this is a little bit of a combinatorics. So this point is a distance 0 from the first vertex. It's sitting right at the vertex, right? So it is somehow, I'm writing this loosely, this symbol, right? It's the value, the 0 order derivative at that vertex. And so this one, ooh, that's just, that's definitely, sorry, this is a typo. Let me go to the picture. Okay, so let me just look at the picture and tell you which information is what. So if we're sitting here, right, this is combinatorial distance 1 from V1. So this coefficient is, again, loosely associated, loosely meaning in the same sense as Taylor expansion, almost, right, with the first order derivative at this vertex. Also, if you wish, right, it's at the combinatorial distance 2 from this vertex, which means I can loosely associate this coefficient with the second derivative at this vertex, okay? If I'm looking at this point, it's, actually a better one. This point is also at distance 0 on the edge, right? So I can associate it with the value on this edge. Again, it's a loose association, but that's how we think about that. All right, so each point here can be associated with the value on the edge, and that's actually a univariate spline. The restriction is a univariate spline. You don't need any B-spline basis here. You can just interpolate. All right, and this point could be, again, it's a distance 2 from this vertex, so you can use the second derivative at this vertex. When I say the second derivative, I mean the full second derivative, all the information. You also need the first, but again, it's a loose association. There's a nice formula. And this idea that the coefficients are associated not with some information, some data at some strange origin, but with the data that is sitting right on the triangle, allows to glue those things together because the information, they share the information, so to speak. right? Because if this is my value at this point and there is a neighboring triangle, I'm going to use the same value and it's going to give me C0 right away. So that's basically the idea of Bernstein-Bezier basis. Okay, so that's for 4. So so here's we have it. So 2 triangles, right? I have my polynomial over 1 triangle. I'm going to call it P. Let's say it's on the top, and the second one is Q, and it's on the bottom triangle. And each one of them has its own basis and its own coefficients. But for example, all the coefficients on the shared edge 1, 1, and 2 over here, right? If I want to make this continuous, they would have to be exactly the same. Because they are, again, they are associated with the values of the polynomial on this edge, nowhere else. And so they have to be exactly the same. All right, that's the continuity. Great. And that is what I just said. Great. Okay, good. So now we look at smoothness conditions, because as we know it, in FDA, we want smooth splines now, right? So how do we build smoothness? And smoothness here is also not difficult. So let me just give you the smoothness condition. Scroll back. So remember, we would like to match the values, which we already did, and the first order derivatives on that edge, right? So question, which coefficients have anything to do with the first order derivative on that edge? Remember, derivative is combinatorial distance, right? So it's first order derivative. So I only have to look at the points that are at distance 1 from this edge. In other words, the main message is that these black points over here and those black points have nothing to do with it. We completely forget about those coefficients. They don't change. They stay the way they are, and you can use them for anything you want. They do not affect the smoothness. Unlike if we're doing it in Cartesian standard basis, then they all will have to change. Here, we don't have to change them. We only look at what is close to the edge. If I want the second order derivative, I would move a little further and involve more coefficients. This is true for the multivariate case. If you're looking at 2 simplices in Rn, and they share some kind of, m-1 or any other simplex, okay? And you're building 2 polynomials, and you want to know which parameters interact, which parameters have to be glued together. All you have to do is to look at those that are at combinatorial distance less than 1 from that facet. And this is plain combinatorics. You can code all of this by looking at the subindices. You don't have to worry about any, meaning of it. Okay, so the conditions. So what are the smoothness conditions? And the beauty is that it's a very sparse matrix. In fact, there is not a single huge matrix at all. We're going to have, in this case, I'm just going to show you the quads, right? So they will be, so this is 2 polynomials of degree 4, and the derivative is going to be, is it 4? 1, 2, 3. Degree 4, right? Okay, great. So we are going to have 4 equations, and each equation is going to have 4 unknowns, all right? So this is one equation, I'm showing you, this is a linear equation, and it's going to have 4 unknowns. This is the second linear equation, another 4 unknowns, so they're quadrilaterals. Okay, it's a very sparse system. They're linear equations, and in fact, geometrically, I'm going to say it, I'm not sure if it's relevant, but I will say that. So the equation itself, it's a homogeneous equation, where all these 4 control points will have to be on the same plane. There are 4 points, right, in R3. They don't have to be on the same plane. But if we want to make it smooth, they're going to be on the same plane. And I think I will demonstrate it on the one-dimensional case, which is a little nicer and it looks better. And we will look at the parabolas again, okay? The same 2, the same 2 parabolas, right? So let's say we solve the problem, but now instead of, A, B, and C, we're doing this in Bernstein-Bezier form. right? Then there will be 3 domain points. There's a domain point, domain point, domain point. Okay, it's a simplex, remember, right? It's a one-dimensional simplex. So for parabolas, I'm going to throw in 3 domain points on each. And then there will be control points, and there will be one control point, another control point, one more control point, this control point, and this control point. And if I ask anybody who is from the spline community, they will tell me right away that the spline is not C1, right? Just by looking at these points. And they know why, right? So how do we know that these are the coefficients, right? How do we know that this is not a C1 spline? Because we know that there is a simple condition that these 3 points would have to lie on the same plane. So in other words, if my third point is here, that is C1. So that is what we're trying to pursue when we're saying, like, how do we check the smoothness conditions? We want to check it in a very simple way, and that's how we do it. We look at whether or not they lie on the same, in this case, plane or hyperplane. And if you want a higher smoothness, then we would like these points to lie on the same polynomial surface, the same quadratic or the same cubic, and so it goes. Again, this is true in any spatial dimension for any number of coordinates. Okay, great. So this is done. Okay. So this is a demonstration of this in 2D of the same idea, right? So by looking at these control points, the spline community will say, yeah, I mean, this looks like it's a C1 spline, right? We don't even need to see the surface because these 4 points lie on the same plane and the next 4 points lie on the same plane. And so it goes. And Min Jun, who just left, he has a paper, which I think is one of his best papers written about probably 30 or 25 years, a very long time ago. But he sort of, you know, imagining points on the plane is easy, but if you're thinking about C2, right, then you have to imagine a quadratic surface, and that's hard. I mean, just by eyeballing it, you would not be able to tell if it's quadratic or not, right? But he actually managed to do it in terms of planes. It's a very interesting paper. I like this paper. I'm not going to talk about it, but there's a simpler way to visualize this, and you can see it even for quadratics and cubics and so on and so it goes. All right, so great. I think I talked about this. So what's the basis for us now? That is the question, right? So this is the last question that I'm going to address. What do we use instead of B-spline basis? So for example, if I'm looking here, what's my basis? I'm going to choose this function, this function, this function, but I cannot choose that one because as you can see, they're clearly linearly dependent. So that's out of the basis. And I'm gonna add this one. To us, this is the basis. We call this a minimal determinant set. From these linear equations, we can easily deduce the basis. You can certainly write it explicitly if you want to. But again, for us, the basis is associated with a subset of domain points, not with functions. It's a discrete set of points, and each point carries an information, some combinatorial information about how far it is from the simplex and what it can do, what kind of information it can interpolate or approximate. And the dimension, of course, it's the same vector space, mind you. Whatever B-splines would span, these guys span as well. It's the same space. It's a linear algebra problem, right? We change bases. But this information, the BB basis or Bernstein-Bezier basis carries local information. It carries information about how far it is from the boundary and what kind of data it can interpolate or approximate, and what is more reasonable information for that. So I probably will, but just in case, I mean, since this has no numbers, right? So what is this? That is a C1, C3, right? 1, 2, 3. All right, so this is a C3, one of the C3 smoothness conditions, right? And this is one of the C2 smoothness conditions. So just by looking again at the combinatorial distance, you can decide what kind of smoothness or what kind of information is encoded there. All right, so what else? I'm not gonna say anything. This is how the books are written. Carla talked about. This is actually what Carla said pretty much. By the way, yes, whatever Carla did with her error estimates, right? It's exactly for quasi-interpolation. Basically, it's one-to-one. You can do it in the multivariate case, which I won't. I think I'm just going to probably stop right there. I'm not sure if it's important in this community. Yeah, that probably. Yeah, so this is what we do with BB basis. Basically, so far, this is what we have done. So we can create finite elements because they carry the information about the boundary, the data on the boundary. They're more efficient in computations and they're local. Yeah, and I think that's where I'm going to stop.